This chapter is about thermodynamics. We've already talked a little bit about thermodynamics when we talked about enthalpy. Enthalpy, if you'll remember, is H. Sometimes we call Q. It's equal to pretty much the heat that's being released by a reaction or being absorbed by a reaction. We use it to predict if something's exothermic or endothermic. So we're going to be talking about enthalpy in this section along with a few new things, entropy and free energy. We're going to start with the first law of thermodynamics, which is the law of conservation of energy. In a chemical reaction, energy is neither created nor destroyed. It can get changed from one type of energy to another, so it can change from like potential energy to heat energy, but it isn't created, it isn't destroyed. There's a few terms in this chapter that we need to be familiar with. The first one is spontaneous. One thing to know is spontaneous does not mean fast. Spontaneous just means that it's something that happens without any kind of outside intervention. So it happens naturally, but it could be fast, it could be slow. Rusting is a spontaneous process. It occurs naturally without any kind of extra help from me or anyone else, but it takes a long time to happen. Spontaneous reactions go in a very specific direction. If you go in a other direction, they are considered non-spontaneous, so they don't occur without outside intervention. You have to do something to make them happen. Another term we need to be familiar with is reversible. A reversible reaction we already know about, something you can shift to make it go back the other direction. These are things that we can get to return to their original state by reversing our process. Irreversible processes are things that once they've reached a certain point, they are not going to go back to the way they were unless you do a lot more to them. Irreversible processes are going to be spontaneous processes. So a spontaneous reaction like rusting is irreversible. You can't take rust and turn it back into iron. And then a third term we need to know is isothermal. Isothermal is a term we may have seen in gas problems before. This is just any type of reaction that's occurring when there is a constant temperature. Next thing we're going to look at is the second law of thermodynamics. The second law of thermodynamics is all about entropy. Entropy is another thermodynamic function. It is abbreviated with the letter S, and it's a measure of how random or disordered the system is. It's all about randomness and disorder. If you have something that is increasing its disorder, then it has a positive change in entropy, a positive delta S. If you have something that is becoming more ordered, it has a negative delta S. Entropy is a state function. And a state function is something that it doesn't really matter how you get there. When you're at a certain point, the object will have a certain value. So a good example of this is if I take a box and hold it above the earth at a certain height, it has a certain amount of potential energy. It doesn't really matter how the box got there. I could pick it up and put it there. I could pick it off a shelf and put it there. It doesn't matter how it gets there, just once it's at this point, it has a certain amount of potential energy. That's a state function. Enthalpy was another state function. There are lots of state functions, and entropy is one of them. Spontaneous reactions tend to favor increases in entropy. That means that reactions that tend to happen easily without any outside help tend to cause more disorder or more randomness within their system. You can relate entropy to enthalpy like this. You can use this equation right here. Now we're going to see a different equation here in a little bit to use for the relationship between entropy and enthalpy that's a little bit better. The change in entropy is the main type of entropy we're going to talk about. Just like with enthalpy, it's really hard to measure an exact entropy of a system at any point in time, so instead we talk about the changes in entropy. The second law of thermodynamics is also called the law of entropy, and pretty much it states that anytime you have any type of natural process, it is favoring an increase in entropy. So things like to move towards randomness and disorder. It's the second law of thermodynamics. So my classroom is messy, not because I am messy, but because my classroom is obeying the second law of thermodynamics. It is moving increasingly towards a state of disorder and randomness. So for spontaneous reactions, since entropy is always increasing, that means the change in entropy must always be positive. It must have a total increase in entropy. For reversible processes, the change in entropy tends to be 0. For irreversible spontaneous processes, change in entropy is going to be positive, greater than 0. Now, to understand some parts about entropy, we need to understand a little bit extra about molecular motion. Molecules tend to undergo 3 different types of motions: translational, vibrational, and rotational. So we need to know the difference between these. Let's say that we have a little water molecule, and our water molecule is water vapor, it's gaseous. Okay, the molecule is going to bounce around, it's going to move around. Okay, this is called translational motion. However, the atoms within the molecule are also going to vibrate back and forth towards each other, away from each other. This is called vibrational motion. And the molecule can also rotate around. This is called rotational motion. And all particles have all 3 types of motion. Gas particles are going to have more of some types of motion than like a solid particle will. But all 3 of these types of motion are always present. And if you take into account all 3 of these types of motion, then what you're taking into account is something called a microstate. A microstate is kind of a combination of all the kinetic energies that occur because of these motions, and even some potential energies as well. Now, your book goes through and talks about the relationship between W, which is the microstate, and entropy, and it has this wonderful little equation here with Boltzmann's constant, which we'll talk about later, but you are probably not going to see that very often, so that's not something I would worry about knowing. What you do need to know is make sure you know what a microstate is, how it's determined, and what it has to do with entropy. Pretty much the more microstates a particle has, it means the more motion it has, then the more entropy it's going to have. And you can increase the number of microstates that are available for something by doing things like increasing its temperature. You increase its temperature, it's going to have more motion. You can also increase its volume, give it more places to go. You can also increase how many of them there are. All of these things will increase the amount of microstates available to the system. And as a result, since you're increasing the number of microstates that are available, you are increasing the entropy. So changing things like increasing the temperature, increasing the volume, and increasing the number of particles all increase the amount of disorder that the system has. Now, you can also increase the entropy of a system by doing something like dissolving it in water. You dissolve a solid into water, you're taking a solid from its nice little crystal lattice structure and you're dissociating it. You're totally filling it up with randomness, and so you're increasing its entropy if you dissolve it in water. Now, something that's really interesting, though, is once those little ions get into the water, they attract the water molecules to them, and so the water molecule's entropy actually decreases. And if those attractions get large enough, usually with pretty highly charged ions, then the overall net change in entropy will actually be a decrease in entropy, even though you're dissolving the solid into the water, which is doesn't happen very often, but it can happen. Other things that can also increase entropy are things like state changes. A solid change to a liquid is more disordered. A liquid change into a gas is more disordered, so that's an increase in entropy. You forming any kind of liquid or solution from a solid, or if you increase the number of gas molecules that are present, you have 1 mole of gas turning into 2 moles of gas. That is an increase in entropy as well. Now, what you guys will often be asked to do is to predict qualitatively whether or not delta S is positive or negative, or if it's undergoing an increase or decrease in entropy. So let's see how to do that. So here you have liquid water turning into gaseous water. So since it's going from a liquid to a gas, that means it's increasing its disorder. Since it's increasing its disorder, that means delta S is going to be positive. Here on the next problem, we have aqueous ions coming together to form a solid. It's a precipitation reaction. In this case, our substances are becoming more ordered. So entropy is decreasing, and our change in entropy is negative. Here we have a solid and a gas turning into a solid. So we have a gas turning into a solid. It's an increase in order, so it's a positive delta S. And here, this one's very interesting. Here we have gases turning into other gases, and we have 2 moles of gases turning into 2 moles of gases. This one, the delta S, is kind of up in the air. Delta S is going to be pretty darn close to 0 in this one. It's probably going to be a little one way or the other, so it might be a little positive or a little negative, but it's impossible for us to really tell given the information that we have here. And then lastly, we have the third law of thermodynamics. The third law of thermodynamics states that if you have a perfect crystalline structure at 0 degrees Kelvin, that this perfect crystalline structure is going to have no motion whatsoever, because it's at absolute 0, and therefore it is going to have no entropy whatsoever. So theoretically, we can have a substance with 0 entropy if it is has absolutely no disorder in it whatsoever. The last thing we need to look at, anytime you have a phase change, you have really big jumps in entropy. Entropy always increases when you increase temperature, but when you hit a phase change, you have a really big increase in entropy.